practice problem 13.1.1. We're going to go through all 4 steps, and we're going to create and interpret a confidence interval. So that's part 1, the 4-step hypothesis process, hypothesis testing process, and part 2, which is the confidence interval. All right, it's going to be a bit of a voyage, but bear with the process and learn something along the way. If you haven't watched the first 4 videos, or 5 videos rather, about creating a hypothesis for a 2-sample t-test, then you probably should do that first. Here we go. So it looks like Pat wants to compare the cost of 1 and 2 bedroom apartments. She's looking at the area around her college campus, and she collects data from 10 random samples of advertised apartments for 1 bedrooms and 10 for 2 bedrooms. So here's what we've got. She's got 10 2-bedroom apartments and 10 1-bedroom apartments, got their prices, and she's wondering if 2-bedroom apartments are significantly more expensive than 1-bedroom apartments. We're going to perform a significance test to answer her question, and we're going to do the 4 steps. So, step 1. I'm going to identify my population / populations, since this is a 2-sample test. We are going to find out what we're truly talking about. That's the parameter. Our null hypothesis and alternative hypothesis. And though it doesn't specify an alpha, that means we get to pick our own, and let's say a 5% significance level. Okay, so population. This would be all 1 and 2 bedroom apartments near her campus. The parameter is going to be the true difference. In dollars. So how much difference is 1 and 2 bedroom apartments? My null hypothesis is that 1-bedroom apartments are the same as 2-bedroom apartments. The alternative hypothesis is that 1 bedrooms are less expensive than 2-bedroom apartments. All right, there it is. That's all we need to start our problem. Step 2. Step 2 is our conditions. And remember, we need to have both populations, both 1-bedroom and 2-bedroom in this context, identified that they satisfy all conditions. So I'm going to say 1-bedroom and 2-bedroom as far as my conditions are concerned. And then I will lay out a simple random sample for both, normality for both, and independence for both. So simple random sample. In the problem, it said she took a random sampling of advertised apartments. So it was stated for both 1 and 2-bedroom apartments. Normality, however, it didn't say the prices were normally distributed. I don't think. Let me check again. Nope, it doesn't say that 1 and 2-bedroom apartments are normally distributed, and she only took a sample size of 10, so that doesn't satisfy the central limit theorem. So for both 1 and 2-bedroom apartments, we have to assume normality. For independence, our population has to be 10 times bigger than our sample. Population 10 times bigger than our sample. And I think it's safe to say that there's more than 100 2-bedroom apartments and there's more than 100 1-bedroom apartments around a college campus. That's makes sense to me. So I would say all 1-bedroom apartments is indeed greater than or equal to 100, and all 2-bed apartments is indeed greater or equal to 100. So we should be good to go there. All right, step 3, calculations. Now in this particular problem, they gave us a list of values. I dropped those values into my calculator and, hold on, my dog's whining. Hang on, just be right back. Get out of here. Sorry about that. Anyway, I dropped the values into my calculator of the 1-bedroom and 2-bedroom apartments, and our goal here is to use that, and we can use the data category when using our calculator here. But first, let's set up the equation so we can show that we know what calculations are going on behind the scenes. So if we recall, it is because we weren't given a population standard deviation, it's a t-test. So I'm going to put that up right up there. It's a 2-sample t-test. And the formula for that is t equals the sample mean of 1-bedroom apartments minus 2-bedroom apartments divided by the standard deviation of the difference. That's the sample standard deviation squared of 1-bedrooms over the number of 1-bedrooms plus the sample standard deviation squared of 2-bedrooms over the number of 2-bedrooms in our sample. Okay? If I drop those numbers in, well, first of all, I have to get those numbers. And so in order to do that, I would run a 2-variable stats function on L1 and L2, and that gets me a mean, so I would say x sub 1 equals a mean of, let's see, what is it? A mean of 531 for the 1-bedrooms with a sample standard deviation of 82.8. And for 2-bedrooms, it would be $609 with a sample standard deviation of 89.3. So we can see that it looks like 2-bedrooms are more expensive. Of course, are they enough more expensive to show that there's a difference between these two? Let's drop those values in and run the calculation on RTI. So if I just were to put the numbers in, it would look like this. T equals 531 minus 609 divided by the square root of 82.8 squared over 10, that's my sample size, plus 89.3 squared over 10, again, my other sample size. Now, I'm not going to do that in my calculator in the sense that I'm punching in the numbers and going to drop that in. Instead, I'm going to go to a 2-sample t-test, that's function number 4 on my calculator in the stats test menu. And I'm going to say, let's use the data that I dropped in already. So what does that tell me if I want to know if 1 is less than 2? In the question of pooling, select no, do not pool your data. Just go ahead and calculate, and here's what we've got. It gives us a p-value of 0.029. That's from a t of negative 2.02. So we're over 2 standard deviations below the mean, and the probability of that happening is quite small. I'm going to leave those values there for step 4, our conclusion. All right, here we go. Step 4. Big finish. Remember, our conclusion needs to have three parts. We need to show evidence. We need to make a choice to reject or fail to reject. And lastly, we need to put that in the context of the problem. Well, our evidence is this guy right here. It looks like the probability of this difference of 0.029 is indeed less than our alpha that we selected at the beginning of the problem, 0.05. Less than means our choice is to reject the null hypothesis. What was our null hypothesis? The null hypothesis was that the two averaged to be the same. So we're rejecting that. So context, it seems that our alternative was that one bedrooms were less than, so that's what we're going to use. One bedroom apartments are less expensive than two-bedroom apartments. Okay, so one bedrooms are less expensive than two bedrooms. Certainly not shocking results here, but nice to know that there is indeed a significant difference. The question remains, though, how much of a difference between one-bedroom and two-bedroom apartments? And once we know that difference, we can say, hey, is it worth getting a two-bedroom apartment? So let's go on and create a confidence interval. That's part 2 of this practice problem. All right, so confidence intervals part 2. We're going to lean heavily on our calculator, but first let's set up the confidence interval formula. So it looks like this. Remember, we're looking at the difference between one-bedroom and two-bedroom apartments. And we want to know the range of that difference based on our confidence interval, our confidence level. I think we'll pick 95%. So I'm going to take a t-star because, again, I didn't know the population standard deviation, and that is times the standard deviation of their differences. Standard deviation squared of the first apartment over its sample size added to the standard deviation of the two-bedroom apartments and its sample size. Dropping in some values here, I'm going to have to remind myself of what this was. I think it was 531 minus 609. Let me just make sure here real quick. Yep, 531 and 609. Plus or minus t star. Now t star for a 95% confidence interval with 9 degrees of freedom, remember our sample size minus 1, can be found using our table C right here. It'll also pop up in your calculator if you run the confidence interval function. So degrees of freedom, 9 degrees of freedom, 95% confidence interval. I'm just going to bebop on up here, and it looks like that is 2.262. So 2.262, standard deviations up and standard deviations down from the difference times, looks like my one-bedroom apartments were 82.8 squared over my sample size 10 plus standard deviation of my two-bedroom apartments was 89.3 squared, and my 10 two-bedroom apartments all square rooted. And this is a calculation that's happening when I do a two-sample t interval in my TI calculator. What is the two sample t interval? What comes out? What's my low value and my high value? Well, it looks like this. All right, so my confidence interval says it's negative 158.9 to 2.9. 95% confident that the true difference between one bedroom and two bedroom apartments is between, let's get this in the context that it's meant, between $158.90 less for a one bedroom to $2.90 more for a one bedroom. So it looks like a 95% confidence interval actually gaps that there is no difference. That'd be zero in this interval. No difference between the two. So we're getting a little bit of conflicting information from our interval, but remember intervals are two-sided, so that makes sense. So it looks like one bedrooms in general are going to be less than two bedrooms. But maybe not that much less, and in some cases, maybe one bedrooms are more. But I guess that makes sense. Maybe there's a really nice one bedroom as compared to a really shady two bedroom. So there we go, all of problem 13.1.1, and I kind of verbally gave the context of this confidence interval, so be sure to write that out. I am 95% confident that the true difference between one and two bedroom is between 158 less and about $3 more for a one bedroom. Hope this helped.